Hello, and welcome to my talk on sampling query variations for learning to rank to improve automatic Boolean query generation in systematic reviews. My name is Harry Scells. This work was completed as part of my PhD at the University of Queensland in collaboration with CSIRO. Before we begin, I would like to break down the title of this talk. And I'd like to break it down into three main points: systematic reviews, automatic Boolean query generation, and sampling query variations for learning to rank. I will first provide some background on these 3 points, and then I'll cover the contributions of this research, which relate to the third point, by investigating our proposed methods, analyzing our experimental results, and then identifying future research. So let's have a look at the first point, systematic reviews. A systematic review is like a literature review. They are the synthesis and appraisal of all relevant documents for a particular research question. They also aim to be unbiased and comprehensive. They also must adhere to strict guidelines and protocol, and this ensures the review can be reproduced. On the right is a high-level overview of the systematic review creation pipeline. There are many steps in this pipeline, but here it's been simplified as a funnel, where a research question comes in the top, and then through a series of stages, a systematic review is produced. Studies are gradually refined through retrieval, study appraisal, or in other words screening, and synthesis to just maybe a handful of studies in the end. But there's a big problem here, because all these processes are time-consuming and expensive. At a high level, this research is looking to reduce these costs by improving query formulation. This brings us to the second point to cover: automatic Boolean query generation. In previous research, we've developed a model to fully automatically refine an existing query into a more effective one. By refine, I mean modifying the query in some way in order to reduce the total number of studies retrieved, but maintain recall. A simplified description of the way this model works is by first generating candidate variations. These variations are generated by modifying a single aspect of a query. Next, one candidate is selected by ranking the variations and then taking the candidate most likely to be the best refinement. Finally, this process of query candidate generation and query candidate selection is repeated to form a chain of transformations, where the end is the final chosen query. The final point to cover is query variation sampling, which is the main focus of this talk. Our model to automatically refine queries uses learning to rank for the candidate selection process. However, first a learning to rank model must be trained. The way we obtain training data for learning to rank is to automatically generate variations of queries. Unfortunately, this process is computationally infeasible, as the space of query variations, even for a single query, is astronomical. Therefore, we must sample the variations in some way to reduce the computational load. And this leads us to the motivation of this talk, where I ask, does the way training data gets sampled affect the performance of candidate selection? It also leads me to define sampling and selection. When I refer to sampling, I mean training queries. And when I refer to selection, I mean queries chosen by a learning to rank model which have been trained on sampled queries. This brings us to the research questions we set out to investigate as motivated by this question. The first research question aims to identify if the choice of sampling strategy has a noticeable impact on the effectiveness of sampled queries. The second research question aims to identify if the choice of sampling strategy impacts the effectiveness of the selected queries. And the third research question aims to identify if any relationships between the sampled queries and the selected queries exist. The main contributions of this work are the ideas of exploration methods and sampling strategies. An exploration method is how the query variation space is navigated in order to drive sampling. In this work, we have 2 exploration methods, a breadth-first approach and a depth-first approach. The breadth-first approach pools queries at each step in the chain, and we have a parameter to control how many queries we sample. In the depth-first approach, the query space is traversed using a depth-first search, and a cost-based approach using the chain of previous queries is used to control the number of queries sampled. Then we have a number of sampling strategies, which are instantiations of an exploration method, and determines how queries are sampled. The table on the right presents the sampling strategies that we investigate in this work. Unfortunately, there isn't enough time in this presentation to cover all of them, but in the next slides, I hope to provide some intuition for both how exploration methods work and how some of these sampling strategies may drive them. First, I would like to explain breadth-first exploration. Given an original input query, all of the variations for this query are generated. Only one aspect of a query is modified at a time to produce variations. A portion of these variations are then sampled as indicated by the red circles and solid lines. New variations of the previously sampled queries are then generated, and again, queries are sampled. This process continues again until a certain depth is reached. The random sampling strategy using breadth-first exploration method should then be quite intuitive. It simply samples queries randomly each time variations are generated. A slightly more complicated sampling strategy, such as evaluation positively biased, drives the exploration of query space by only sampling queries that are the most effective in terms of some evaluation measure. Depth-first exploration works very differently to breadth-first exploration. First, a single variation is generated for the input query. This particular query happens to meet the criteria to continue the search. Then, from this query, the search process is continued, and new queries are examined, until the next query that meets the criteria for continuing the search is found. This search is repeated until another criteria for stopping the search is met. At this point, all of the queries that match the search criteria are sampled, and the process continues from the original input query, until the next query that meets the search criteria is met. Note that it is possible for two queries at the same depth to meet the same search criteria, and the depth that the search stops for a query is not the same for all queries. To give some intuition on how sampling strategies drive this exploration method, you could consider them to be the criteria for choosing which queries to explore and the criteria for when to stop searching. For the random sampling strategy, for example, the criteria for continuing and stopping the search is controlled by the roll of a dice. Now, with an understanding of how query exploration methods work and sampling strategies work, I'd like to present the results of these methods. First is the effectiveness of sampled queries obtained by applying each sampling strategy. This figure only shows the overall effectiveness of queries that were sampled. We show this to demonstrate that each sampling strategy samples queries differently. We found that sampling using breadth-first exploration in combination with a sampling strategy that positively biases queries with precision, obtains the highest average F1 score. We also found that there was no correlation between the number of samples and the average F1 score. This suggests that scores are not influenced by the number of queries sampled. However, the choice of sampling strategy does affect the sampled queries. Next, let's look at the effectiveness of those queries selected by learning to rank models trained on different sets of sampled queries. We found that sampling using a combination of breadth-first exploration and sampling by diversifying the top-scoring queries provided the most effective selected queries. For positively biased sampling strategies, we found that depth-first exploration provided more effective selected queries than breadth-first. The highest performing selected queries were chosen not by biasing query effectiveness alone, but in combination with diversification. Note that very small differences in effectiveness can have a significant impact on the total cost of the review, upwards of hundreds of thousands of dollars. Finally, we investigate one of the relationships between sampled and selected queries. Here, we're looking at the most effective and least effective queries chosen by breadth and depth first exploration. The least effective selected queries, those on the right, are weakly positively correlated with sampled queries, while the most effective selected queries, those on the left, are moderately positively correlated with sampled queries. This suggests that sampled queries do indeed impact the model used to select queries. And to summarize this talk, we found that sampling does indeed impact the selection of queries, that diversification provides the highest gains in effectiveness, and that the small gains we see can have significant time and cost savings for systematic review creation. The end goal of this line of research is to integrate it into tools for people to use to assist them to formulate more effective queries. Thank you for your time and attention. I'll now be available for questions online and afterwards via email and Twitter.